Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. This episode examines the reason for and the timing of the rat deployment on Air India Flight 171. This analysis does not seek to assign blame to any party. Instead, it aims to distinguish between the confirmed evidence, the plausible hypotheses, and unsupported claims. We will examine three possibilities: a spurious deployment of the rat, human action from one of the pilots, or an automatic system response, and test each against the recorded timeline. The preliminary report states the aircraft air-ground sensors transitioned to air mode consistent with liftoff at 08:08:39 UTC. The aircraft achieved the maximum recorded airspeed of 180 knots IAS at 08:08:42. And immediately thereafter, the engine 1 and engine 2 fuel cutoff switches transition from run to cutoff within a time gap of 1 second. And the engine N1 and N2 rotational speeds began to decrease from their takeoff values as the fuel supply to the engines was cut off. The CCTV footage obtained from the airport shows the rat getting deployed during the initial climb immediately after liftoff. The aircraft started to lose altitude before crossing the airport perimeter wall. As per the EAFR data, both engine N2 values passed below minimum idle speed, and the rat hydraulic pump began supplying hydraulic power at 08:08:47. Let's start with the takeoff and examine the 17 seconds to the airport perimeter wall. The distance is 1,390 meters, which implies an average ground speed of 158.9 knots, or an average airspeed of about 164.8 knots, assuming a headwind of approximately 5.9 knots. The preliminary report states that the calculated V speeds for the conditions were V1 at 153 knots, VR for rotation at 155 knots, and V2 at 162 knots. The Flight Radar 24 timing aligns with both the FDR and the ATC timing in the preliminary report. Now let's take a look at the wind data. So during the critical period around 08:08 UTC, the wind is reasonably bounded, the speed between 3 and 7 knots, and the direction between 240 and 260 degrees. And based on this, the estimated airspeed at the airport perimeter wall is approximately 144 to 151 knots indicated airspeed. This is below the reported V2 of 162 and is consistent with both the meteorological information and the preliminary report's observation that the aircraft had begun to lose altitude before crossing the perimeter wall. At this point, we need to be precise about what fuel cutoff means. The fuel switches command full engine shutdown. The FADEC data link loss commands engine to idle to avoid uncommanded or asymmetric thrust. A flameout is the loss of combustion in an operating engine typically due to interruption or airflow disruption. Following fuel cutoff, combustion stops and the engine begins to spool down. The rotating core, however, does not stop immediately. Airflow continues to drive it, a condition known as windmilling. In this state, the engine is no longer producing thrust, but it may still be capable of a relight if fuel and ignition are restored, while sufficient rotational speed remains. Now let's look at the aircraft's energy state and climb performance. Rotation occurs at approximately 080835 at about 155 knots indicated airspeed. Liftoff is recorded 080839, 4 seconds later. The calculated V2 is 162 knots. At 080842, just 3 seconds after liftoff, the aircraft reaches a maximum recorded airspeed of 180 knots IAS, and that is well above V2. This indicates strong initial acceleration and positive climb performance immediately after liftoff. However, this trend does not continue. By the time the aircraft reaches the airport perimeter wall, the estimated airspeed has decreased to approximately 144 to 151 knots indicated airspeed, which is well below V2. This implies that from 080842 onwards, the aircraft is no longer gaining energy. Instead, it is losing airspeed and experiencing a degradation in climb performance, consistent with the observation that the aircraft began to lose altitude before crossing the perimeter wall. In other words, within seconds of reaching a speed well above V2, the aircraft transitions from a positive energy trend to a negative energy trend. Flight Radar 24 reports pressure altitude, not true geometric altitude. And with a QNH of 1001 HPA, the runway itself corresponds roughly to 515 feet pressure altitude. That means the reported post-takeoff values of 575 to 625 feet indicate the aircraft was only about 60 to 115 feet above the runway on a pressure altitude basis, or roughly 60 to 120 feet after allowing for the hot 37 degrees centigrade conditions. This is far short of the several hundred feet of climb that would be needed to offset the later loss of airspeed from 180 knots to about 144 to 151 knots. So the available data remain consistent with a degradation in both speed and climb performance. The preliminary report does not provide time-stamped altitude data, so it is not possible to determine precisely what altitude was reached at specific points during the flight. This limits the analysis of the aircraft's total energy state and climb performance. In particular, the exact timing of any loss of thrust cannot be determined from the available data and can only be constrained to a broad time frame. According to the preliminary report, the RAT was deployed immediately after the transition to air mode at 080839. The aircraft speed reached its maximum value at 080842 just 3 seconds later. Then immediately thereafter, the engine 1 and engine 2 fuel cutoff switches transitioned from run to cutoff, one after the other, with a time gap of 1 second. The engine N1 and N2 began to decrease from their takeoff values as the fuel supply to the engines was cut off. And as per the FDR data, both engine N2 values passed below minimum idle speed. The aircraft is estimated to have crossed the airport perimeter wall at 08:08:56, based on the Flight Radar 24 ADS-B data. And the aircraft started to lose altitude before crossing the perimeter wall. Here's what we know from Hamilton Sundstrand, the RAT manufacturer, and from their documentation. The RAT module has a generator, a hydraulic pump, a strut assembly, a frame assembly, a deployment actuator, and a turbine assembly. When deployed, the turbine assembly extracts energy from the airstream and drives the generator and the hydraulic pump. The generator driven by the turbine provides approximately 10 kVA at 230 volts, three-phase. The hydraulic pump is a variable displacement 5,000 psi unit capable of delivering approximately 10 gallons per minute, GPM, at 4,850 psi and 19 GPM at 2,700 psi, which is at the minimum governed turbine speed. The unit is installed in the aft right wing body fairing, aft of the right main landing gear wheel well. A RAT compartment door is mechanically linked to the RAT strut lug and opens as the unit deploys and locks into place. The RAT module has a line replaceable pressure transducer, which provides a signal when the hydraulic pump is delivering pressure to the aircraft hydraulic system. This was the signal with the hydraulic pressure very likely received at around 08:08:47. Captain or first officer can deploy the RAT manually by pressing ram air turbine switch on the overhead hydraulic panel. The RAT can also be deployed automatically if electrical or hydraulic power is lost. For loss of electrical power, each bus power control unit, BPCU, signals RAT deployment from the Common Computing System, CCS, about 15 seconds after either continuous loss of 235 volt AC on both the main L1 and the backup buses, or a continuous loss of 235 volt AC on the backup bus and the left auto transformer unit contactor, the LATEC, is open. CCS will place RAT auto deploy command on the common data network for use by hydraulic systems and auto deploy function. And 200 milliseconds after signal from the BPCU, hydraulic controllers will command the RAT to deploy. The main battery bus provides 28 volt DC at 4 amps for 3 to 5 seconds to power the RAT solenoid. The deploy command causes the uplock mechanism to release the RAT. The spring-loaded deployment actuator forces the rat to extend into the airstream. There is a snubbing action of deployment on the actuator, which dampens deployment as the rat nears full deployment. And then the downlock engages. Turbine index plunger is automatically pulled as the rat nears full deployment position, a maximum of 72.5 degrees, and unlocks the turbine blades. And the airstream causes turbine assembly to rotate and begins providing electrical and hydraulic power. Let's have a look at the reasons for rat deployment. The rat serves as an emergency source of electrical and hydraulic power, and there are no operating time limits or airspeeds or altitudes. Firstly, manual deployment. Captain or first officer need to just press the switch on the overhead hydraulic panel, and the rat is deployable even when the airplane is on the ground. Automatic deployment. In flight, the rat deploys if both engines have failed, all three hydraulic pressures are low, loss of electrical power to the captain or first officer's flight instruments, loss of all four electric motor pumps and faults in the flight control system on approach, or loss of all four electrical motor pumps and engine fails on takeoff or landing. The term engine failure is used here in the system sense, as defined by the Boeing flight manuals. It does not necessarily imply mechanical damage. Irrespective of the aircraft electrical configuration, if both engines' main bus fails, then the rat is deployed, with primary power unavailable regardless of rat availability. The main battery relay closes to power the captain's instrumentation tie contactor and the first officer instrumentation tie contactor. Main battery provides power to captain and first officer's bus until rat is deployed, but only the captain's instruments and displays and not the first officer's instruments and displays are powered during this phase. The command to deploy the rat can come either from the left or right Common Core System, CCS, or either the left or right Bus Power Control Unit, BPCU. Now, very importantly, there are time delays in the rat deployment. 200 milliseconds after the signal from the BPCU, the rat will deploy. Each BPCU independently requests rat deployment from R2 15 seconds after either continuous loss of 235-volt AC. Transition to air mode occurs 1 second plus or minus 0.1 second after any airspeed parameter is greater than 80 knots, or any VFSG speed, that's the variable frequency starter generator, is greater than 10,500 RPM. An airspeed determined from all three corrected airspeed parameters delivered via the core data network. And the VFSG speed is determined from each of its generator controller units. Rat auto-deploy is inhibited when not in the air mode. In other words, at least 80 knots of airspeed or any of the VFSGs has moved from starter mode to generator mode. The rat deployment event is analyzed under three possible causal origins: spurious, human, or system-driven. The rat deployment event itself does not determine its cause. Its meaning is derived from its timing, the sequence, and the system context. The extremely short interval between liftoff and rat deployment, around 3 to 5 seconds, makes a manual deployment pathway operationally unlikely. During the rotation and initial climb phase, when crew workload is at its peak and attention is focused on flight path control. Within this time frame, the crew would have had insufficient time to perceive, diagnose, and respond to an abnormal condition by activating the rat switch manually. Historical operational evidence indicates that spurious rat deployments are typically isolated mechanical or maintenance-related anomalies and are not associated with immediate loss of propulsion or catastrophic flight outcomes. In contrast, the AI171 event sequence includes a near-simultaneous dual-engine fuel cutoff, a rapid thrust decay, and loss of control culminating in impact approximately 31 seconds after takeoff. This combination of timing, system behavior, and outcome is more consistent with an automatic system response to a severe aircraft state condition than either a manual or a spurious deployment. While a spurious deployment cannot be categorically excluded, it would require an independent failure occurring coincidentally with the dual-engine fuel cutoff sequence, which is considered less probable. The time taken for the rat to come online electrically and hydraulically is dependent on the aircraft indicated airspeed in the slipstream. The rat deployment is spring-loaded and takes less than 1 second to extend completely. The time for the turbine to spin up to operating speed can take around 10 seconds. The gearbox increases the turbine speed by a ratio of 2.13 to 1 to drive the generator. We can estimate the time it takes to reach the minimum turbine speed to permit hydraulic operation and the time it takes to reach the minimum turbine speed to permit electrical operation. During acceleration, the hydraulic pump is temporarily offloaded by the volume fuse, which means the turbine is allowed to spin up before the pump is asked to do full work. Hydraulic operation begins first, about 2 to 4 seconds after blade release, or roughly 3 to 5 seconds from the deploy command in a normal indicated airspeed case. At the minimum governed turbine speed, the pump can deliver about 10 gallons per minute at 4,850 psi and 19 gallons per minute at 2,700 psi. That tells us the certification relevant hydraulic capability is tied to a turbine speed threshold, not directly to an IAS threshold. And this is the key hydraulic threshold. That tells us there is a defined turbine speed threshold for serviceable hydraulic output, but the manual does not publish the corresponding IAS. The generator is not connected immediately. The rat contactor closes only when the generator reaches 380 Hertz. The gearbox increases the turbine speed by the ratio we mentioned, 2.13 to 1. Electrical operation begins later, about 4 to 8 seconds after blade release, or roughly 5 to 9 seconds from the deploy command. Near the lower end of the rat operating envelope, it would take about 6 seconds as a conservative upper estimate for the first useful hydraulic output, and about 10 seconds for the electrical cut-in. One more useful inference is that the 380 Hertz threshold may be treated as a synchronous cut-in point, and then the corresponding generator speed would be about 11,400 RPM if the rat generator were four-pole, and 22,800 RPM if it were two-pole. And using the gearbox ratio, we're talking then of a turbine speed of about 5,350 RPM for a four-pole generator and 10,700 RPM for a two-pole generator. But that RPM estimate depends entirely on pole count, and the documentation does not state the rat generator pole count. We can turn this into a step-by-step deployment timeline, starting from the hydraulic or electrical loss detection, the BPCU CCS command, the rat release, the blade unlock, the first hydraulic pressure, and the generator cut-in at 380 Hertz. So what does all this mean? The preliminary report timeline only shows the rat hydraulic pump began supplying hydraulic power. It does not show the electrical cut-in, and that is critical. From the manual, electrical requires preset generator speed of 380 Hertz. That is a higher threshold than initial turbine rotation. The implication: hydraulic power is available early and electric power later. The approximately 150 Hertz tonal spacing observed in the Facebook reel is physically consistent with the blade passing frequency of a two-blade 50-inch Boeing 787 rat turbine rotating at about 4,500 RPM. And using the Hamilton-Sundstrand gearbox ratio of 2.13 to 1, this corresponds to a generator speed of about 9,600 RPM. This is a plausible rat operating condition and strengthens the interpretation that the recorded harmonic structure is rat-related. The Hamilton-Sundstrand training labels the Boeing 787 rat as a 50-inch turbine, which is reasonably interpreted as a 50-inch rotor diameter. For a rotor of this size, the blade tip sonic speed occurs at approximately 5,160 RPM under standard sea level conditions. If the 380 Hertz threshold is interpreted as a generator synchronous cut-in, then a four-pole generator implies a turbine speed of about 5,350 RPM, corresponding to a tip speed of approximately 356 meters per second, or Mach 1.04. This lies close to the sonic threshold and is mechanically plausible for a deployed rat. By contrast, a two-pole generator implies a turbine speed of about 10,700 RPM and a tip speed of approximately 712 meters per second, or Mach 2.08, which is substantially above the sonic regime and far less credible for this application. On this basis, the 50-inch turbine geometry materially favors the four-pole interpretation over the two-pole interpretation. The preliminary report states the rat became hydraulically effective at 180 knots IAS, and this is within the strong dynamic pressure regime and expected 3.0 to 3.6 seconds after the rat deployment command. Most likely rat deploy command window was 080843.2 to 080843.8. And the most likely full extension and blade unlock window was 080843.9 to 080844.7. The key implication is that if hydraulic power is recorded at 080847, the rat was probably already physically out and unlocked roughly at 080844 to 080845, while the remaining time being turbine acceleration to the minimum hydraulic operating speed. That aligns with the fuel switch movement from run to cutoff, and quite precisely. The recorded timing is therefore most consistent with a rapid loss condition, most likely hydraulic or electrical collapse, rather than the 15-second sustained electrical loss logic described for the BPCU. The Hamilton-Sundstrand statement about a 15-second delay applies only to one specific electrical loss pathway, not to every auto-deployment case. The rat deployment is therefore consistent with an immediate condition trigger rather than delayed pathways. Out of the various conditions for rat deployment, both engines having failed is the best fit. This is the strongest fit to the timing and to the event sequence. It does not require waiting for a slower secondary degradation path, such as a sustained bus logic or a progressive hydraulic depletion. A dual engine failure trigger is exactly the kind of high-priority emergency condition that would be expected to command rat deployment essentially immediately. All three hydraulic pressures low is the second best fit. This is plausible, but weaker than both engines failed. Engine-driven hydraulic output would begin collapsing once both engines were no longer producing power. The center hydraulic is not engine-driven, however. It is driven by an electric motor pump. If the three hydraulic systems decayed very rapidly, this could trigger rat deployment on a short timescale. No documented automatic deployment pathway other than the immediate condition triggers is consistent with the observed 3 to 5 second deployment window. So in summary, we know from the preliminary report that both engines flamed out and relight sequences were initiated. The airplane was not merely seeing a switch movement or a transient configuration change. It was in an actual dual engine failure state, which is exactly one of the explicit RAT automatic deployment conditions from the Boeing FCOM. There are two automatic command sources for deployment, the high diff and the BPCU. And within the automatic logic, the high diff appears to monitor several aircraft state conditions, including loss of all engines, both engines less than minimum idle, loss of all hydraulic power, and loss of all electrical power. But those four conditions are not equivalent in timing. We can constrain the window, but we cannot yet order every internal event inside that window. Within a very short interval after liftoff, multiple events appear to have occurred in close succession or partial overlap. A possible FADEC data link effect with the fuel metering valve movement toward idle, the fuel switch recycling, engine shutdown, RAT auto deployment logic, and the initiation of relight logic. On the presently available record, the precise internal order of those events cannot be established. Loss of all engines. This is the best candidate for the earliest high-diff driven deployment path because it can plausibly be recognized as soon as both engines are no longer producing thrusting power following the dual fuel cutoff event without waiting for N2 to decay all the way below minimum idle. A slightly later trigger, both engines less than minimum idle RPM. This is almost certainly later than the loss of all engines because spool down has to occur first. The preliminary report itself supports that sequence by stating that the engines N1 and N2 began decreasing after fuel was cut off, and later notes that both N2 values pass below minimum idle. And potentially later still, loss of all hydraulic power, left, right, and center low pressure. This may also lag the initial engine power loss, depending on pressure decay rates, accumulators, and the center system behavior and logic thresholds. And finally, the electrical path. The Hamilton-Sundstrand BPCU sustained electrical loss path with an approximate 15-second delay does not fit the observed 080847 sequence. The available evidence supports a narrow cluster of interacting events and a rapid automatic RAT response, but does not yet permit a definitive ordering of every underlying control, switch, FADEC, and relight event inside that cluster. So what is our conclusion? The available evidence is most consistent with a system origin event. The available timing evidence suggests that the most consistent RAT auto-deploy initiator was the high-diff monitored system-level condition loss of all engines. The condition both engines less than minimum idle is also consistent with the event sequence, but it necessarily occurs after a finite spool-down interval and is therefore more likely to represent a subsequent confirming condition rather than the earliest deployment trigger. Loss of all hydraulic power remains plausible, but is more threshold dependent, while the delayed loss of all electrical power described in the Hamilton-Sundstrand material is a poor fit to the observed short timeline. The loss of all engines condition is most plausibly derived from discrete engine state signals, such as fuel control switch position or FADEC shutdown status, rather than from analog parameters such as engine core speed decay or hydraulic pressure loss. In the present case, the transition of both fuel control switches from run to cutoff constitutes a discrete digital event that would be immediately available to aircraft systems. Even allowing for minimal processing latency, such a signal would be detected significantly faster than conditions dependent on engine spool down, hydraulic decay, or delayed electrical loss logic. This provides a consistent explanation for the rapid RAT deployment observed in the preliminary report, with the hydraulic output established at 08:08:47. So the bottom line, in my view, discrete engine state signals appear to fit the observed timing better than any decay-based conditions. And that concludes my analysis of the RAT deployment. If you enjoyed this investigation and episode, then please subscribe for future investigations on both Air India, MH370, and shortly we'll be introducing other aircraft investigations which still remain unsolved. Thank you very much for watching, and have a good day.